My name is Prof. Joyce, and today I'll be discussing about your double indicator titration. And online, I have seen some discussions on this, but I think it's not extensive enough. Basically, here I'm going to discuss 3 possible scenarios. And this involves, again by its name, 2 indicators. Double means 2, indicator, and the word titration. So what is really happening here is you have a setup, a titration setup. So I would like to apologize ahead of time. I don't really excel in drawing, right? And so can you just imagine this is a straight burette? Okay? Let's just assume this is a good burette, okay? It's straight. And we have here on the bottom, you have your conical flask. So again, this is your titrant. Okay, you can remember that one. Top titrant, and on the bottom you have titrand, D for down. Now, what really happens here is you are considering a special mixture of bases. Again, your sodium hydroxide is a strong base, and your sodium carbonate here is actually a weakly basic salt. So what is happening in the first scenario is we have this consideration. NaOH is not exposed to the atmosphere. How would you know that's the scenario? If you read the question, you have here a statement. A 1.2 gram sample of a mixture of sodium hydroxide and sodium carbonate. It contains certain impurities, okay? They're dissolved. If I want to draw this one, you have a 1.2 gram sample, and basically this is in combination of 2 chemicals. One is NaOH, your sodium hydroxide, and the other one is your sodium carbonate, right? And so what you want to see later on is the percent purity of each, all right? Now this is the premise. You are titrating that sample with 0.5 normality HCl. So this is acidimetry, right? You call this acidimetry since your titrator or your titrant is an acid. Now you have 2 indicators here. The first one is phenolphthalein and the second one is methyl orange. Remember, your phenolphthalein, it will undergo a color change depending if it's in acidic environment or basic environment. But basically, if we are to trace it from, let's say, from acidic, or let's make it opposite, from basic to acidic pH. If we have that kind of pH change, then you would expect that your phenolphthalein will basically change from pink to colorless. That's the color change that you will see if you're from a basic solution to an acidic solution, from pink to colorless. Now for your methyl orange, if we are to consider, okay, this part here, if we are to go from basic to acidic pH, the color change will be different. It will be from yellow to pink. And so when we perform double indicator titration, what we are actually waiting for is this endpoint, the phenolphthalein endpoint going from basic to acidic, so the colorless is what we want to see. And after we attain that, after we see your phenolphthalein changing, that's the time wherein we add your methyl orange indicator, and again, add enough of your titrant, in this case HCl, so that we could see a color change from yellow to pink. So the methyl orange endpoint here should appear pink solution. Now, in this scenario, if you read it, you already know it's 0.5 normality HCl with phenolphthalein as the indicator. It's the first one, okay? The first volume that you add towards your phenolphthalein indicator would be 30 ml. So let's write that down here. So for the volume of HCl, in order for you to achieve the phenolphthalein endpoint, you need how much? 30 ml, according to your problem. So 30 ml. Now, after adding, let's just see, no? This is 0, for example, and then you add your acid up to your 30 ml mark. So this is the part consumed by the first volume, right? So I hope you understand. Now, you stop at the 30 ml mark because you see the colorless solution, the formation of this one. So it would signify, okay, we have achieved the phenolphthalein endpoint. We have to stop and then add your methyl orange this time. Now, when you added your methyl orange, okay, so that's the second indicator, it took you another 5 ml. So let's just put it here. Assuming this is 5 ml. That's the volume you added in order for you to achieve your methyl orange endpoint. Again, let's write it down here so it's clear. So for the methyl orange endpoint, you added 5 ml. So that's the volume. But later on, if you want to, how do I say this? Solve for the percent purity. Remember the equation for percent purity during your titrations is percent purity of a substance is equal to volume times normality times your MEQ weight divided by the weight of your sample times 100. So later on, we need to find 2% purities, that of your NaOH, and the second one is that of your sodium carbonate. Right. Now the problem is this. You know the normality, right? The normality is given here. Your MEQ weight is easy to find. You just have to solve for the MEQ of your sample here. For example, NaOH. Let's write that down here. So all the data that we know so far, okay, let's write it down here. So for the percent purity, let's be clear on this. This one is for the percent purity of your NaOH. Let's write it down here. Well, obviously, you need to look for the volume first. You don't know how much, right? And the normality is already given. It's 0.5. So let's write it down here. 0.5 normality. Now, the next question is the MEQ weight. Again, whatever is your sample here that you're looking for in terms of purity, you'll be using its MEQ weight. Sodium is 23, oxygen is 16, and hydrogen is 1. So that gives you 40 as the molecular weight. Again, just in case you don't know, the molecular weight of your sodium hydroxide is 40 gram per mole. Now, given that it's 40 gram per mole, you have to find the MEQ weight, and that's easy. All you need to do is to get the molecular weight divided by the number of equivalents. Since it has one OH for the bases, you just have to count the number of hydroxide. The number of equivalent is 1 times your 1000. Milli. That's why you have to divide this one by a factor of 1000. And then you have your sample here. In terms of weight, it's 1.2 gram. So I hope you see the picture here. What we're actually looking for is your volume. And it's not what you expect, right? You can't really use 30 ml straight ahead. Why? You have to understand how our chemicals are changing when we're performing titration. In this case, there is such thing as double equivalence points. So how does this look like? You start with, again, NaOH is not exposed to the atmosphere. It retains its chemical identity. So you have here, let's take for example, you have a mixture. And then you have your sodium carbonate here. They're independent, okay? They're here, but they're separate. I hope you get the idea. When you add the first volume of HCl, in this case it's 30 ml, when you're adding that, remember it's a strong acid and this is a strong base. So let me label that for you. Strong acid. This one is a strong base. This one is not so strong. It's actually, let's just write the word weak base to indicate the difference between them. So this is strong and this is a little weaker than this one. When you add the first amount of HCl, HCl being strong will first fully neutralize your strong base. Remember that. So here, it will become your neutral salt. NaCl, your table salt, is neutral. So let's put the word here, neutral. Okay. And in this part here, in the side, right, they're separate. You are expecting that this is now complete. So let's indicate complete neutralization. So that's complete neutralization. That is what's happening here. Now, what about for your sodium carbonate? What happens when you first add your HCl? It will now undergo what you call your half neutralization. Remember, this is the same addition of acid. But what happens on the other side is it becomes sodium bicarb. Sodium bicarbonate. Right? And remember, your sodium bicarbonate is not neutral. It's actually weak, but it's weaker than this one. Your H is acidic. It indicates that your HCl is acidic. And this H is being taken up by your sodium carbonate so that it can form your bicarb, meaning to say, it gains this hydrogen, indicating that from weak base, it becomes weak. So that's just for the magnitude, for the sake of magnitude. This is double weak compared to this one and to this one, right? But it's still basic. At this point, you call this your half neutralization. So let's put the fraction here, 1/2. So where is the other half? That will now be the second part of addition. Remember, from this point to this point, okay, are you following? From this point to this point, the formation of your sodium bicarbonate, this is actually your phenolphthalein endpoint. And here, you can see your phenolphthalein from pink, it becomes colorless. Remember, from a basic salt, it becomes less basic upon addition of acid. Right? So in short, from basic, it becomes less basic. Therefore, towards acidic pH. And that's why here, you're seeing a change from pink to colorless. And that's the time you add your methyl orange. And now it becomes yellow. Okay? Now you add more acid. Second addition. Let's put it here. When you add your HCl on the second level, second addition, this 5 ml here is enough to show your methyl orange endpoint, which is actually this one. The conversion of your sodium bicarb completely to your neutral salt NaCl. So at this point, if this is the half neutralization stage, this now becomes your complete neutralization. And since this is the first half, the other half would be this part. And so what is this part here? This is your methyl orange endpoint. So what you're seeing here is from a basic pH to completely neutral. So again, the direction here is from yellow to pink. It's losing its basicity in the process of neutralization. That's why you'll know you'll stop when you see your pink solution, right? So let's label this one, okay? At this point, you have to know the first addition, which is 30 ml. What is covered here is this entire process on top. So the HCl here is enough to neutralize your sodium hydroxide and to half neutralize your sodium carbonate. That's your 30 ml. The second addition is this one, the 5 ml, which is enough just for you to neutralize fully your sodium bicarb to its salt, sodium chloride. Again, this is 5 ml. Okay? So I hope that's clear to you. Now, if this is 5 ml, if this part is 5 ml, this part, and this is the half neutralization, the other half is this one, it would mean, therefore, that for this part alone, let me mark that for you, this part alone is also 5 ml, right? So later on, when you're trying to solve for the purity, percent purity of NaOH, what is the volume now? That's your question. Looking at this diagram, if this entire top process requires 30 ml, and you only want to use the volume required for your NaOH, your sodium hydroxide, but the problem is the entire here on top requires 30 ml, it would mean to get this portion alone, the volume needed for your sodium hydroxide, you need to deduct this part. You don't want this part, right? The 30 ml is this part, but that's considering that you need that ml for the both sodium hydroxide and sodium carbonate. Now, if you're looking for the purity of sodium hydroxide, you need to isolate only the volume needed for this part. And so if you know this is 5, and the top portion here is also 5, 30 minus 5 will therefore be the volume. So here it's 25, right? 30 minus this part here, which is 5, 25 ml. So now that's your solution for your percent NaOH. So let's just ignore the units for now because we don't really have the space. So this is 0.040 divided by 1.2 grams. By the way, you have to multiply this by 100 because it's in percent. Okay, so times 100. I forgot to tell you. So now you will be getting an answer of 25 times 0.5 times 0.040 divided by 1.2 times 100, giving you 41.67%. Okay, so that is for your NaOH. Now, how about for your percent sodium bicarb? Again, this is easy. If you are looking for the percent purity of sodium carbonate, you will still use the same formula, but different volume. So let's consider the scenario. You want to look for, let me erase this bit here. Okay, let's erase this one since it's obstructing our view. Okay. At this point, you have to look for the percent purity of this one. And that process is from this part until this part, until it becomes completely neutral. All the volume you need for that process, that's the volume for your sodium carbonate. So now it's clear to see. If this is 5, then this is also 5. So the volume now is 10, right? From here to here is 5, another 5 to complete. So the volume here is 10 ml. 10 ml, still the same, 0.5 normality. This time it will change since you're looking for the sodium carbonate. Remember, you have to get its MEQ. So 23 times 2 for your sodium plus 12 from your carbon, 3 atoms of oxygen, that's 16 times 3. You will be getting a number, 106. Let me erase this bit here. This is 106. Again, the number of equivalence here is 2 times 1, positive 1 sodium. So here 2 times 1, that's 2. 2 equivalents times 1000. Since it's milli equivalent, divided by your sample weight, which is still 1.2 grams, times 100, since it's in percentage, and that would give you how much? 10 times 0.5 times 106 divided by 2000 divided by 1.25 times 100. You should be getting a number 21.2%. Again, 10 times 0.5 times 106. Let me get this one first. I'm not really sure if I did it correctly. Okay, so I'm right. This is 106 divided by 2. Okay, so I'm right. 0.5. I'm just checking in my calculator. Right, 21.2%. So the answer here is therefore this one for sodium carbonate and this one for your sodium hydroxide. That's the first case, not exposed to the atmosphere. So if you want to see the second step, the second scenario, just watch the next video.